Hi, everyone. Welcome to my session on serverless machine learning. My name is Asavri. I'm a product manager on Azure Functions. I do language extensibility and experiences for the product. Mostly, I'm just a Python enthusiast trying to make the language more and more relevant in the Azure cloud. Most recently, I've been spending a bunch of time playing around with data science and speaking to customers about why serverless is relevant for the machine learning workloads. So I figured I'd get on stage today to share some of the learnings that I've had from these engagements and just findings in general. All right, so the plan for today is to first go over a little introduction of what machine learning is. There's a lot of buzz about AI and ML and what it means, so let's go ahead and set the context for the purpose of this session. We'll then look at how there are still challenges with machine learning and how serverless and functions as a service can help with some of these challenges. And then dive into a few real-world use cases of serverless machine learning. Finally, we'll take a look at some of the learnings from the use cases that we're going to see and challenges that are yet to be conquered. So let's go ahead and get started. First off, what is machine learning? The textbook definition is machine learning is the practice of examining vast amounts of data to find patterns and then using or generating code to find those same patterns in brand new data. Broken down into simple language, really, machine learning is no different from human learning. So for instance, if I showed you this image and said this was an apple, and so is this and this, you'd know that none of these are an apple out of the picture here. So really, what we're trying to say is machine learning can help you build smarter applications. So let's look at what the process of machine learning looks like. Really, I divided it into two components, training and deployment. We'll take a look in just a second. The very first part, model training. Training starts with data. The more data you have, the better your results are going to be. And no data actually is always in its prepared format for you to examine. It'll contain things like duplicates, conflicting information, missing information, and needs to be processed with data preprocessing modules to bring it to a state so that your application can start consuming it. The next step, once you get prepared data, is to find the right statistical algorithm to train your application. A data scientist would typically experiment with different aspects of the data, different combinations of prepared data and algorithm to see what gets the best results. And really, once we go ahead and apply a statistical algorithm to prepared data, what we get as a result is a candidate model. And you might have heard this term a couple of times. A model is nothing but a piece of code that is trained to find patterns in data. Once we've got a data, the next step is to go ahead and deploy it to create an application. If we don't deploy an application, everything that we've done in terms of training is pretty much useless. So it's important that we're able to easily and quickly deploy the model so folks who are actually training the model are able to iterate and update fast enough. That's the second component. It's called model deployment. Interestingly, these two, model training and model deployment tasks in machine learning, are actually performed by two different roles. While model training is typically the job of a data scientist, and we already spoke about some of the questions that a data scientist would need to answer, things like how much data do I need, what algorithm I should use, is my data processed and prepared enough, so on and so forth. Model deployment is the job of an application developer. Naturally, this is because not only do you have to take the model and deploy it, you have to answer a bunch of infrastructure-related questions, things like, what's the scale going to look like? What platform should my application run on? How many servers do I need? What about the monitoring? What packages do I need to install on my servers? All of which are very uninteresting to a data scientist. Good for us, serverless replaces all those questions with complete abstraction of servers and flexibility in terms of deployment. So much that we feel that model deployment with serverless can actually be performed by the data scientists themselves after they train the models. And this is really what serverless machine learning is: deploying a model as a serverless application in order to create an inferencing pipeline is what we're referring to as serverless machine learning. So let's take a look at some of the use cases of serverless ML. The very first one I want to talk about is that of image classification. So interestingly, we actually had a customer who wanted to build an inferencing application using the TensorFlow library of Python. They already had a trained model. They simply wanted to deploy it so it can start to take input in the form of images over HTTP, and then go ahead and run a prediction to classify that image into one of the categories that they already had. The very first thing that we experimented with was a PaaS solution, a platform as a service solution. So assuming that we already have a trained model, in order to deploy that model as an inferencing application, the very first thing we do is to go ahead and add a scoring script. And a scoring script is basically nothing but a Python script that knows how to get a prediction out of a model. Once we've got the scoring script, the next task is to go ahead and containerize this application, add the right version of the functions of the Python runtime, production WSGI servers such as Gunicorn, and any dependencies or packages that are required by our application. Once we've got the container, we can go ahead and deploy it to multiple instances of app service, and then we'll likely set up an application gateway to load balance the incoming traffic. Now, let's take a look at the serverless solution. Once I've already got the model and the trained model and the scoring script, all we need to deploy this as an Azure function is to go ahead and add configuration details in terms of the trigger that will invoke our application and any dependencies that we need in order to actually run the Python script. And we can deploy an Azure function. So pretty fundamental use case, very basic, but there are some key learnings here. Very quickly, we learned that Python is key to machine learning inferencing pipelines. In this specific case, since the customer walked up with a pre-trained TensorFlow model, we wouldn't have been able to build the application if Azure Functions did not support Python. Second, even outside of the event-based scaling itself, the functions programming model is very valuable to folks like data scientists who aren't really traditional developers. The functions, triggers, and bindings model provides a great way for you to be able to speak to multiple data sources without having to get into the nitty-gritty details of the underlying SDK or authentication mechanism. And finally, serverless provides a great low-cost solution for event-driven pipelines. So you no longer need to provision a load balancer or a traffic manager. You can simply rely on consumption scaling in order to scale your applications. OK. The next use case I have is that of topic modeling. And this one, the customer basically wanted to set up an inferencing application that would take as input a bunch of raw data in the form of IT FAQs, correspondence, troubleshooting guides, and go ahead and classify it into multiple topics that text contained. Slightly different from the previous use case we saw, because this one also had an additional component to it, which was a retraining pipeline. So not only did they want to get new data or new input and go ahead and make a prediction on it, they also wanted to use the new data to go ahead and retrain and update the ML model. Let's take a look at what the serverless architecture for this problem would look like. And the very first component of our serverless solution is a one-time training pipeline. So what we basically did was took a bunch of raw data and set up a function that would take as input that raw data, go ahead and use the Spacey and NLTK modules to go ahead and clean all the noise and lambertize those words, and then finally use GenSim to produce a trained model. We can go ahead and store the trained model in blob storage, and as a side effect, also store the clean data in Cosmos DB data store. The second component was to actually set up the inferencing function that would take this trained model and be invoked on any new input data that it saw, whether this was over an HTTP request or blob storage, et cetera, and run a prediction to produce output in the terms of the topics that were actually predicted over that input text. And then the third component is actually pretty interesting. It's a retraining pipeline. So we set up a third function that would also be invoked on the new input that we saw. It'll go ahead and grab the cleaned data from the Cosmos DB store and go ahead and use GenSim to perform the LDA topic modeling algorithm, and then finally update the model that was in BlobStore. So learnings from this one. The very first one, going into this use case, we were actually pretty skeptical about whether training is a good scenario for serverless or not. And became clear pretty quickly that high compute training scenarios are definitely not something that work for serverless. But there is a certain category of scenarios that are short-lived executions and can perform well on low compute as well, such as the text processing example that we just saw, that are still very much feasible with serverless functions. Second one, in this architecture you saw we were orchestrating with blob storage and Cosmos DB. Interestingly, with the Azure Functions triggers and bindings again, you no longer have to worry about the SDK or authentication mechanism for those data sources. Especially helps data scientists code their scoring scripts without have to learn a bunch of development or SDKs, and they can just start to grab input from various data sources in order to actually perform the prediction. And the third one, this one's actually a downside that we discovered, that in a pipeline where your model is actually not packaged up with the function application itself, you're probably downloading it from an external storage source, such as Blob in this case, which definitely increases the time that it takes for your application to start up. And that's a performance constraint that you need to be aware of if you're setting up a retraining pipeline of this kind. All right, and then the third one. A little bit similar to the very first use case we saw, but slightly different in the way we actually ended up implementing it. So let's take a look. Our use case was basically OCRs, so the customer had a bunch of images of vehicle number plates, and they wanted to go ahead and convert these into machine-readable stream of characters. So what we did was set up an application so that when one of these new images is uploaded to Blob Store, it'll go ahead and trigger an event grid. And those of you not familiar with event grid basically provides an event routing service, which has a uniform event consumption infrastructure based on the pub-sub model. So once we go ahead and trigger the event grid, it can in turn go ahead and make a call to a logic app, which is basically a workflow orchestration engine and has the ability to call multiple first and third-party Azure and SaaS services. What the logic app would do is first go ahead and call an Azure function. And this is so the Azure function can actually reshape and transform the image into a format that's consumable by the rest of our application. It'll then go ahead and use the processed image to make a call to cognitive services, the computer vision API, which will provide out-of-the-box ACR based on the transformed image, and finally go ahead and write the results to a storage queue. Learnings from this one. The key learning from this one is serverless, even beyond functions, is very relevant to machine learning workloads. In this specific example, we saw eventing orchestration, that's workflow orchestration, and pay-per-use cognitive APIs. And really, functions in this entire architecture plays the role of being the glue that ties together multiple different serverless services. Right? And then we already saw the learnings from our different use cases. The next one that I do want to touch upon are some challenges that we saw that may not have been directly apparent from the architecture diagrams that we're seeing. The first one, serverless does impose limits in terms of the total execution time or memory available to your function. So if you do have a function that runs, say, longer than the 20 minutes timeout, there are options. I know Azure provides the dedicated or the app service hosting plan. If you do have a function that's running too long because it's orchestrating or managing various other functions, you can use features like durable functions as well. The second one, some inferencing workloads we realized do have requirements for more powerful hardware. They need either GPU or FPGA-enabled hardware to actually perform the execution. Again, for this one, since the Azure Functions runtime is completely open source, you can actually go ahead and containerize the Functions runtime and your function application to go run on a GPU-enabled Kubernetes cluster. You would still get the same exact programming model, but now you're hosting on a container hosting service with the hardware of your choice. Third one, we realized data science teams really like to version their models independent of the inferencing application or the inferencing code itself, which is challenging because if you saw the second use case, the model was actually stored in blob and caused a negative impact on the performance of our entire application. One of the options that you can consider here is to go ahead and deploy your own custom container to Azure Functions, so in which case you can pretty much pull your function application code and the model from different sources while you're updating and deploying a new image. And then finally, as you start to deal with data, there is more and more requirements in terms of security and networking options. And you do need to cater to things like VNet requirements, network isolation, et cetera. With Azure, you do have the option of running your functions in an app service environment for full network isolation, or even on the premium plan if you want to keep your functions hidden away from the rest of the public internet. All right, a few takeaways. The very first one I want to emphasize is serverless is indeed a good fit for machine learning. Even outside of the event-driven scaling itself, the functions programming model and the event-driven pipelines are very valuable to folks like data scientists who are not traditional developers. It can really help them do a job that they aren't used to or need to get help from mainframe application developers to do. And then finally, machine learning and data scientists are one example. As the serverless community, we should continue bringing the goodness of serverless to more and more scenarios and developers as much as we can. And that's it. Thank you for taking the time. Hope you have.
Would you like to answer some questions? Or rather not?
How are we doing on time?
We're good on time. Anybody have a question for Avasari? Speak into the microphone, please.
Sure. A few slides back, you showed this containers solution with Linux. In that case, are you still getting the scalability of functions, or are you then also running functions runtime on the Linux container?
This was the first use case you're talking about, where we created a Docker container and deployed.
No, just a few slides back. If you go back. If you can.
So there are two container options, basically, that I showed or talked about. One is, since the Azure Functions runtime is open source, you're free to go ahead and run it on any platform and containerize, go run it on your own container hosting service. The other one that I talked about was, we've got two deployment methods with functions. One is hey, bring in your function code, and then we'll host it out of the box on our platform. You don't have to worry about whether it's running on a container, VM somewhere will take care of it. It's completely serverless. The other option that we have is bring in a container, and this works if you have some custom dependencies, like you have an apt-get package that's not available on our platform, or you're bringing a custom version of the runtime, something like maybe the Anaconda distribution of Python that's very custom to your scenario. So you can bring in a custom image that's hosted on Docker Hub or ACR and actually run it on Azure Functions. Today, you only get CPU-based scaling for that container hosting method. We've got, actually, I don't want to steal Eduardo's thunder, we've got a new plan that's coming up. It's currently in private preview. It's called the Premium Plan, where you actually can go ahead and get event-based scaling like the rest of the functions platform for your custom container. And that's something that Eduardo is going to talk about in the very next talk, actually. Yeah.
Thanks a lot.
Any other questions? Oh, there.
So I noticed you said with the limitations that especially the runtime restrictions that you have might be a restriction. But first of all, I'm a software engineer, not a data scientist. And you talk about basically empowering the data scientists. But for a software engineer, like a runtime being restriction being crossed is a very good reason to think about your architecture and how you're actually doing this. My question here is, would you not then also include more of the software engineering principles within data science as well, if you're going to empower them also to write their own stuff?
I'm not sure I understand the question. It's a question about, hey, how can we actually also combine inner loop, outer loop development practices that a software engineer would typically follow into serverless?
Basically, yeah.
Yeah, so specifically, what I was talking about is how serverless works for machine learning scenarios, but definitely there are options in terms of the developer tooling that you want to use. With Azure Functions, I've said this enough times already, fact that it's open source is one of my favorite parts, because now in terms of inner loop development, you can pretty much go ahead and test your functions, run them locally, debug them, use all kinds of, attach to all kinds of good debuggers. We've got a VS Code story that you like. For outer loop development, there are options depending on what specific features you're looking for. There are options like being able to integrate with DevOps and other CI/CD services, obviously depending on the stack that you're using. So, if you're using Java, to go integrate with Jenkins, there's a plugin that integrates to Jenkins that you can use for your CI/CD workflows. And then there are a few advanced options specifically related to the features that you're looking for. I can talk about this offline if you like.
Okay.
Does that answer your question? Sorry.
I think partially, I think.
Okay.
So maybe one more. Back there.
Let's see if we can throw that far.
Perfect, thanks. Thank you for the talk. You mentioned also in the limitations that there's a security limitation on it. So for the data that's been, sent to the cloud, any particular fields that are more sensible to that? I'm thinking about HIPAA or others that you might want to share.
Mostly the requirements that we see are with the fintech companies. It starts to become more important. That's definitely the most common scenario that I've come across so far. Yeah.
Thank you.
Thank you. Let's give it a